Hello, geometry students. Mr. Zabo. We are going to study 3.5 and 3.6 from our textbook today. The key ideas are overlapping triangles, and then we're also going to start talking about the different types of triangles and specifically how we use them in proofs. Um, we've seen overlapping triangles already, but we haven't had to really make major decisions. So what we need to really understand when we're dealing with overlapping triangles is there's more than just those overlapping triangles. So, for example, what is and what is not an overlapping triangle? This triangle and this triangle are not considered overlapping. They share a vertex, but that's it. Okay? One pair of overlapping triangles here would be this triangle here with this triangle here. Those two triangles overlap. Okay? They share parts of sides, they share different things. With that concept, there's another pair of overlapping triangles in the example on the right. There are one pair of overlapping triangles you can look at here, okay? And there's two pair of overlapping triangles in number 3. See if you can pause the video and come up with overlapping triangles and just kind of shade them over like this. Just do one per diagram. Alright, so take a look at what we have here for our additional overlapping triangles in number 2. There is that only that one pair of overlapping triangles, even though there are other triangles in there. The only ones that are overlapping are those two. One strategy that I would recommend as we are dealing with overlapping triangles and trying to identify specifically as problems like 1 and number 3 when there's multiple overlapping triangles, we're going to get to the point where we're using one of them to prove the other one. It's going to get a little complicated. Sometimes I would recommend doing what I did on the right side here and diagram these separately and then split them up, draw them out. Maybe you have to number your angles, color code them, something like that, so you can visually see where they all match and kind of pull that orange triangle out and look at it on its own. Pull that blue triangle out and look at it on its own. You can compare them that way as opposed to overlapping. Sometimes that's a little bit more clear. All right, so now let's move on to a proof with overlapping triangles. And again, in this case, we can see our overlapping triangles are triangle PWM and triangle TMW, even though we have these two triangles here plus this triangle inside here. The overlapping ones, again, if it's helpful for you, it doesn't hurt to try to separate it out. And you don't have to draw it to scale. It doesn't have to be perfect. But if you can separate these out and label them, that was P, that was W, and that was M, this is T, this is W, and this is M, sometimes that's a little bit helpful for you. Not required, but a strategy that you might want to use. Now we know that segment PW is congruent to segment TM, and I can label that in both diagrams. We know that segment PM is congruent to segment TW. See, that's a little bit easier to label in this diagram. Okay? And the thing is, the tricky part is, I can label that in this diagram, and I can just do this and this. But what's the third piece? So we have these two given pieces. Segment PW is congruent to segment TM, and segment PM is congruent to segment TW. But what's the third piece? Well, in order to prove my triangle's congruent, I have two sides. I would need the included angle, but there's no way I have enough information to prove that angle P and angle T, which are my included angles, are congruent. This is where the overlapping triangle can be helpful. Here I have segment WM, which is actually a part of both triangles. That's the reflexive property. And so we can state that segment WM is congruent to itself because of the reflexive property. And and now my triangles are congruent. Here's again where we've got to be really careful. Naming the triangle. Naming the first triangle is easy. It doesn't matter. Pick a triangle. Let's say I picked this triangle and I called it PWM. Okay. Now what corresponds? I went from P to W, so I have to go from T to M because those are my congruent segments. P to W, T to M, and so it's TMW. Those are three sides. And finally, I have my last statement now that angle P is congruent to angle T. They are in corresponding spots of congruent triangles, so corresponding parts of congruent triangles are congruent. All right, so that's the big ideas for section 3.5, and nothing major new. We need to talk about now specifically are isosceles triangles, equilateral triangles, and then a little bit about scalene, acute, obtuse, and right triangles. Okay, but the key focus is going to be here on isosceles and equilateral. So by definition, an isosceles triangle, and this you got to be really careful, is exactly two sides are congruent. And so in this case, in triangle ABC, what we would say here is that segment BA is congruent to segment BC. Those are, vocab word, legs of an isosceles triangle. AC is the third side, the non-congruent side. It's called the base of the triangle. So when we name a triangle as isosceles, we will oftentimes have to indicate what is the base or what is the vertex. Those are two key words because those are going to indicate which are our legs, which sides are congruent. And angles A and C are also called base angles. One thing I didn't have typed in here, but is also true, our base angles are also congruent. So in this case, angle A and angle C, opposite my congruent sides, are congruent. Angle A is congruent to angle C. So how do we use all of this in a proof? Well, it depends on what we're given. Okay? If a triangle is isosceles, then the two legs of the triangle are congruent and the base angles are congruent. So what we would say is isosceles triangle implies, and we can just literally draw a triangle, and if our conclusion is sides, we would put the two tick marks on the sides. If our conclusion is that those base angles are congruent, we would put the two base angles down here are congruent. That would be our abbreviation for this if-then statement. Okay? If two sides or two angles of a triangle are congruent, then it is isosceles. So if we show that two sides are congruent or that two angles are congruent, we can conclude that it is isosceles. Okay, so that's going beyond CP/CTC. And then if two sides of a triangle are congruent to each other, then the angles opposite those are congruent. So this is using our isosceles triangle properties. If I know in my hypothesis that I have this situation where two sides are congruent, I can conclude that the base angles are congruent. And then the converse is also true. If I know these two angles are congruent, I can conclude these base angles are congruent. Now, it doesn't always appear as I have drawn in those implications here. Sometimes we can rotate those triangles, so my base angles might be here and here, and then we can conclude this is true. So base does not mean bottom. Base just is, by definition, the angles that are along the non-congruent legs. And we've got similar concepts with equilateral and equiangular triangles. In an equilateral triangle, all sides are congruent. Let me mark it this way. And in an equiangular, it's all angles are congruent, and in fact, just exactly 60 degrees. So I know this is congruent to this, to this. they're all congruent, they're all 60 degrees. Okay. They can be applied to any figure where all sides or angles are congruent. So they're interchangeable words. So if a triangle is equilateral or equiangular, then all three sides are congruent. We can make that conclusion. Okay. If a triangle is equiangular, then all three angles are congruent. And I don't know what happened here. Not scientific here, but it works. We can do this. If all three sides are congruent, then all three angles are congruent. So if I know this, and I know this, and then if all three angles are congruent, all three sides are congruent. So those are our if-then statements. Let's take a look at a couple of proofs here. Well, actually, first let's define acute, right, and obtuse. All right, so our quick summary here, acute triangle, all three angles are acute. There's not one angle that's not acute. In a right triangle, one angle is 90 degrees. The key is that the side opposite this 90-degree angle is always your hypotenuse. So no matter how we rotate or reflect that triangle, opposite is your hypotenuse. The other two sides are called legs. And then in an obtuse triangle, exactly one angle is obtuse, the others are acute. So that's how we define acute, right, and obtuse triangles. Now let's look at a couple proofs. So I got this one started. We know that ME bisects segment GO. So that means segment GE is congruent to segment EO. Because bisect implies two congruent segments. Now let's use the fact that it's isosceles. Because it's isosceles with base GO, that's important. GO is the base. That means I can conclude a couple things. First, I can conclude that those sides are congruent. But I can also include that these angles are congruent. So that one given gives me multiple pieces of information. So here's my conclusions, my statements, my conclusions. We got to be really careful. In the first one, I've decided that the legs are congruent. So the isosceles triangle implied this is true. In the second one, the reason is different. I can't write same as 4 because the isosceles triangle has now allowed me to conclude that the base angles were congruent. So I do need two different reasons written out for them. Now I have congruent triangles, and they are triangles. I will name it MEG is congruent to triangle MEO, and I have a side, an angle, and a side. Could we have done side, side, side? Sure. We didn't need to state that the angles were congruent. We could have used the reflexive property. Now that my triangles are congruent, angle 1 is congruent to angle 2 because corresponding parts of congruent triangles are congruent. All right, now we got one more that's a little bit more challenging. I'm going to pause the video, see if you guys can complete this proof. See if pulling out those two overlapping triangles helps. So here's the option I went with. Okay, the key is seeing the reflexive property, then you have congruent triangles. Once my triangles were congruent, and again, making sure you've named them accurately, I did ABC, so then I had to do DCB. Essentially, A has to be in the same location as D, B is the same location as C, and then C at the same location as B. But now that I've proven that, I know that this angle ACB is congruent to this angle DBC. Well, if you look in here, at this angle and this angle are congruent. And if I'm trying to prove that angle BEC here is isosceles, that's enough. Okay. So essentially the way I did it, I didn't need segment AE congruent to segment ED. I could have used that though, because I could have also concluded that segment AC was congruent to segment DB, and then use my AE congruent to DE as a given. So that was CP, CTC, AE is congruent to DED is given, and then use subtraction to prove